Okay, hello everyone. Welcome to another episode in going through a new kind of science and discussing what we have learnt from a new kind of science. For those, it will be the 20th anniversary of a new kind of science, May 14th of this year, and we have been having a 12-week plan of going through the 12 chapters of a new kind of science. And this week we are talking about chapter 6, starting from randomness. So let me start showing you some things here. So here we are on chapter 6, starting from randomness. Now let me explain a little bit about sort of the architecture of the book. The big story is, what do simple programs do, and what are the implications of what they do for creating a new kind of science? The earlier chapters here, the world of simple programs, systems based on numbers, 2 dimensions and beyond, we went through the previous few weeks, and those are about different kinds of simple programs and what they do, the kind of what we would now call the ruleology of those programs. What chapter 6 does is to discuss the question, when we've looked at these simple programs in previous chapters, we've always done them with simple initial conditions. You start the program off with a simple input, you see what the program does when it runs. Chapter 6 is about what happens when you start it off not from simple input, but instead from random input. Now, actually, historically, I studied what's in chapter 6 before I studied most of what's in the earlier chapters of the book. I started looking at the case of random initial conditions back in around 1981. And my original interest had been, how do things organize themselves to make complicated stuff in nature, in the world? And the concept had been that one would start from randomness, and from randomness would come order, and how did that work and what kinds of order could come? But what I then realized, and what was a core sort of discovery in new kind of science, was you don't need that sort of random input at the beginning. It's enough to just have, and as in the crucial experiment, I talk about this, to just have a simple initial condition, just one black cell and a simple rule, and from that to generate what appears to us in many respects to be random. But earlier than that, back in at the beginning of the 1980s, I didn't really know that. And so I thought that you had to start from randomness to be able to produce complexity, so to speak, which turns out not to be true, and that's a big part of new kind of science. But chapter 6 has to do with the question of, well, if you do start from randomness, what happens, and what do you learn about the general character of simple programs from this process of starting from randomness? So in chapter 6, I'm looking at cellular automata again, and I ask the question, what happens when you start a cellular automaton, for example, with a rule like this, from a random initial condition, a random sequence of black and white cells? So in this particular case, what happens is very simple. The system just evolves to a fixed all black configuration. Similarly here, with these other rules, these evolve to just white, just black. These are cases where, so the basic thing that's happening here is, even though there is randomness in the initial conditions, even though we're looking at sort of all possible initial conditions, or we're looking at random initial conditions, we're looking at sort of not a special initial condition, we're looking at an initial condition that wasn't chosen in any particular way, we're getting always the same all black, all white result. Okay, here are some other examples of other cellular automata with different behavior. So what's happening here is you're getting kind of a filtering process going on. You've got this random initial condition, and certain features of that initial condition survive to produce these stripes or these black regions or white regions. But after a short while, the system evolves to a quiescent state. I should just, to set kind of context here, I'm talking in this section about the emergence of order. Even though you start from randomness, you get something ordered. In this particular case, very trivially ordered, it's just a constant setup. In this case, you've got these stripes where you're filtering out isolated ones, in that example, isolated black cells, and that's how you are getting the output. Okay, So now, that isn't always what happens. This was sort of a big discovery of mine from like 1981 type time frame, was you start off from a random initial condition and you generate something which is sort of continually random. It does not end up evolving to any particular simple state. Instead, you're producing complicated behavior, but it's not completely random behavior because it's a cellular automaton rule. So every successive cell has to be determined from previous cells. And that's why you get, for example, these white triangles or these checkered board triangles here. These are all things that once you've got all those black cells there, it's inevitable that they'll all turn white according to this rule. And then that white will get eaten into only at a certain rate by the evolution according to the rule. So here are some other examples of these nearest neighbor, simplest cellular automata, Rule 22, Rule 30, Rule 150, Rule 182. These rules are all personal friends of mine, and they all have this character that you start them off from a random initial condition and they continue to produce randomness. But you can see that kind of the texture of the randomness is different in these different cases. The rule matters, but the behavior is still going to be random. So those are other examples where there are less obvious structures. Okay, and a final case. This is Rule 110. This is a cellular automaton, again, nearest neighbor rules, where even though you're starting off from randomness, you get something with definite structures emerging, but it's a complicated array of structures. There's not something where you just have stripes where there's just a constant thing over time. Instead, you can have structures that move around and do all these kinds of things. So that led, that's just a little bit more on Rule 110. Again, these are pages that are interesting to look at, but were the easiest pages in the book to produce because you just run the computer a little bit longer and there you get the result. Okay, so we just saw kind of informally something which was kind of a big discovery of mine around 1982, 1983 timeframe. The discovery that when you look at different cellular automata, for example, you see 4 characteristic kinds of things that happen, 4 definite classes of behavior. You can classify what happens, the overall behavior of these systems, into 4 basic classes. Class 1, you start from random initial conditions and the thing evolves to a constant state. Class 2, it evolves to a state that is just fixed or simply periodic with time. Class 3, it evolves to something which continues to look random and look kind of chaotic forever. And class 4, you get definite structures which you can identify, which interact in a certain way. So these classes of behavior I first came up with around, I think, 1983. And this is kind of an important way of sort of classifying the kinds of behavior that occur. And as we'll see, in some sense, class 4 is intermediate between class 2 and class 3, at least if you look at kind of families of cellular automata and where these things occur. But in terms of kind of the hierarchy of what's more complicated than what, this is the correct sequence, from the just produces a uniform pattern to a periodic pattern to a random pattern to a pattern with sort of complex structure. Okay, so this is, if we look at lots of different cellular automata, here are examples of the so-called elementary cellular automata, and we just look at these, we'll see that we can tell that these are class 2 examples, that's a class 1 example, this is another slightly more elaborate class 2 example, and here are a bunch of class 3 examples. And then occasionally, like with the Rule 110 here, we'll find a class, here's another type of cellular automaton. These are next nearest neighbor totalistic rules where the value of the next cell depends only on the total values of the cells in the neighborhood on the previous step. And again, even though the type of rule is very different, we can again see this classification. Class 1 evolves to a simple state. Class 2, it produces these stripes. Class 3, continued randomness. Class 4, this kind of set of localized structures. So there's another class 4 rule. So this is, these are yet more, what are these? three color cellular automata. So the main message here is you look at all these different kinds of rules, all these different kinds of cellular automata, starting from random initial conditions, and you have these four characteristic classes of behavior. And it doesn't matter what kind of detailed rules you look at, you still see the same overall classes of behavior. And that will be an important sort of piece of ammunition and evidence for the principle of computational equivalence that I'll talk about later. And that's sort of a core principle for our new kind of science. Okay, let's see, what was the next page about? Let me just remind myself here. What's happening here? Why is this frozen? Oh, there we go. What happened here? Okay, so one of the things to say about this classification is that, you know, at first, I originally found this by just looking at lots of pictures of cellular automata and saying, how can I classify these things? And what's important here is it's like many classifications in natural science. At first you say, is it a bird? Is it a mammal? Does it fly? Does it have fur? Does it lay eggs? Does it do this? Does it do that? It's a classification where then, okay, there are platypuses, there's weird corner cases, but in general terms, there are birds and there are mammals and there are fishes, and it's useful to classify things that way. Similarly, in physics, for example, it's useful to classify things into solids, liquids, and gases, even though there are corner cases of critical points and gels and all kinds of other things, but it's still useful to have that general classification. Why is it useful? It's useful because once you can say, oh, it's a liquid, for example, you immediately know a lot of other things about it. So similarly, once you say it's a class 2 cellular automaton, you immediately know lots of other things about it. And that's what a lot of this chapter is concerned with. Given that you know what class of cellular automaton it is, what are the characteristic features of something like a class 2 cellular automaton or a class 3 cellular automaton? So as we go through this chapter, this is an example of a class 4 cellular automaton doing its very characteristic kinds of things, of having these localized structures, these moving structures, interactions between those structures. This is very typical of what a class 4 cellular automaton does. It's something where there is great complexity in the overall behavior, but you can locally see structured things going on. Here's another class 4 cellular automaton. These are like super fast pages to write when I was creating the book, because all you do is run the program and then you've got a whole page, and it's got more detail than I could probably ever write in, you know, the total detail on one of these pages is very high compared to all the words that I spent a decade writing in this book. Okay, I talk here a little bit about sort of the corner cases, the borderline cases. Is that a class 3 system, or is that a class 2 system? It's got little pieces of class 3 and then there's class 2 outside. It's very similar to the solid, liquid, gas, bird, mammal, fish type thing. There are corner cases, but in general, we can treat this classification as something where we can understand what's going on. What's this? This is asking the question, as we look at, gosh, I forgot I even had this in here. This is interesting. This is a case where we're looking at rules with more possible things to set in them. So this is nearest neighbors, 4 possible colors. So there are a gazillion such rules. There are 4 to the 4 to the 3 such rules, gazillion rules. And so here we can just look at going from one rule to the next and so on. And we're going in steps of 4 because that means that the all zeros configuration doesn't turn into anything different from all zeros if we have codes that are a multiple of 4. And that means we don't get kind of horizontal stripes all the way down the page. But other than that, we're kind of stepping through the possible rules. And what's interesting to see here is that for a while here, the sort of the adjacent rules are all class 2. Then we'll get kind of a class 1 rather. We get a class 2. Okay, there we get a weird one. Then we get a class 4. And then sort of after we go through class 4, we're getting a bunch of class 3 rules, and we get those for a while, and then we'll get different kinds of behavior happening. What we're seeing is, in the space of possible rules, we're seeing something about the distribution of behaviors in the space of possible rules. It's something that's been studied a fair amount now by all sorts of people. And I think it's kind of the precursor of what you need to be able to have sort of a trainable cellular automaton. This is the thing, when you're dealing with a neural net, for example, you have continuous parameters everywhere. So you get to tweak all those parameters separately. In a cellular automaton, you don't get to do that. You just have this one rule. But here, by having a large number of rules, we're getting sort of an approximation to those tweakable parameters. Even in a neural net, you don't really need the full, 16 decimal digit numbers. It's enough to have just a few digits of those numbers. And so that means that you can sort of approximate that tweaking by this a large number of individual states. And so in a cellular automaton, what you're doing is you're approximating. You can do that by saying, let me just look at a fairly large space of cellular automata, and let me then say how what will happen as we sort of step through different rules. Now, obviously, there are different ways that we can lay out the rules in the space of all possible rules. That's something that's interesting that in modern times we think about in terms of rulal space and so on, and in terms of sort of the evolution of the rules. Even the things I've done recently in mathematics make one think about those kinds of things. And actually, we haven't really thought about kind of the genetic evolution of cellular automata. It would be a good thing to think about in terms of sort of a model for biological evolution in which this is the genotype is the code number and the phenotype is the actual behavior. That's something I've thought about quite a bit. But in terms of thinking about that in terms of a multi-way system, that hasn't really been done. Well, okay, so we're talking here about different kinds of systems. Here's an example of where there really is a continuous parameter. This is a continuous cellular automaton, and we're changing the actual value of a continuous variable, and we're seeing sort of transitions from class 2 to class 3 and so on behavior. So again, highlighting this idea that there's this sort of space of possible codes, space of possible genotypes, one might say biologically, and then there's certain classes of phenotypes that populate that space in certain sort of like country borders of those different phenotypes. Okay, and this is showing how you can get class 4 behavior from a continuous cellular automaton. It's kind of a remarkable thing that you can get these kind of persistent structures, even discrete persistent structures, even in something with continuous variables underneath. And those structures arise from essentially kind of homotopic type things. It's as if it's like, the piece of string where you can either wind it around a pencil some number of times, or you can not have it wound around the pencil. That's the kind of thing you're seeing here in the kind of value space of the system. And that's why you're kind of being able to see sort of discrete behavior, even from a continuous underlying structure. Let's see. Okay, so what we're talking about now is what happens. So that was sort of one-dimensional cellular automata. Now we can ask the question, what happens with two-dimensional cellular automata? Do we get the same classes of behavior, or is the story different? So random initial conditions, two-dimensional cellular automata, what happens? So what we're seeing here is kind of the frames in a movie strip. And what we're seeing there is step 1 through step 500 of this particular rule. And we can kind of get some idea there's going to be a class 2-like thing, because it kind of filters itself down to those particular structures. And some other things would sort of filter themselves down to nothing. Let's take a look at something where we can see a more direct comparison, as we did when we studied two-dimensional cellular automata in chapter 5. Okay, those are the final states of some of these different rules. And again, we'll see things which we can pretty much guess are going to be class 1 systems where everything turned white, class 2 systems where there are these isolated blocks, class 3 systems where things continue to look kind of random. And then we're going to see some things like that one is sort of a class 4 example, but we're going to see some other examples of that. Okay, this is how to understand what's going on. These are slices. Remember, we've got this thing in 2 dimensions that's evolving the whole two-dimensional plane is evolving, like you can make a movie out of it. This is now saying, let's take a slice, let's pick the middle of that plane, let's just look at the single line of cells in the middle of that plane, but let's imagine that we're looking in that sort of three-dimensional structure formed by the space-time sort of box, and let's imagine we're looking into fog as we go deeper and deeper, further and further away from the center line, so to speak. And so what we're seeing here is the cells which are black right at the center line are black. The cells which are black further in the distance are a grayer color. And and it's sort of fading to white. Okay, so this is a case where basically we can tell this is a class 2 system. Starts from random two-dimensional structure, and we end up with these just persistent pieces here. So different kinds of behavior. There's sort of the beginnings of a class 3 kind of a class 4 kind of thing going on. That's another case where we're seeing kind of these class 4 structures and a background of sort of just simple kind of class 2 behavior. Here's a famous cellular automaton. This is the game of life cellular automaton. And notice that it really doesn't look that different from these other cellular automata. This is its kind of space-time slice. This is its movie slices. We see here actual structures. Those are little periodic structures. And we see those little trails there. Those are gliders, localized structures that propagate. And we see where are the gliders here? Well, there's a glider there that's propagating. And we can see that's propagating kind of, in that particular case, towards us. Out of the fog and into where we are now, and these are localized. These are repeating periodic structures that we just see in a fixed place, just alternating with time. So that's a case where we see this particular famous cellular automaton that sort of fits right in to our story of class 4 cellular automata and so on. Okay, always remember the notes. So let's take a look here at the notes. Let's take a look back for the notes in the previous section as well. There are all kinds of questions one can ask. There are questions about how does order emerge from disorder? One of the things that I mentioned here at the very beginning, despite initial randomness, processes like friction make systems settle down into definite configurations. Even though you can start them off from all possible configurations and the ball is rolling around in a random, complicated way, friction will make it come to rest. And that idea has been the basis for all sorts of engineering throughout history. This idea in statistical mechanics of law of entropy increase, that there's a tendency for systems to become more disordered, that's an important principle. We'll talk about that more later. But then one can then ask that's kind of a tendency for just the gas to be spread uniformly and randomly in the room. But then there were examples where there sort of seemed to be spontaneous pattern formation, whether it's cirrus clouds, whether it's different kinds of reaction diffusion patterns in biology and so on. These are cases where one went, it seems, from that equilibrium randomness to something more structured. Now, in terms of sort of accounting for how that works in statistical mechanics, there's a whole story of how much energy you have to put in to get to the sort of the thing that has structure. We're not dealing with that here. We're just dealing with the question of how you can start from randomness and spontaneously produce structure. And that's what this is all about. Let's see. This is actually an interesting point that zooming forward to sort of computation theoretic ideas, working out whether a particular substance will be a solid, liquid, gas, or a particular temperature may be computationally comparable in difficulty to working out what class of behavior a particular cellular automaton will exhibit. Given that I just show you the rule, like for rule 110, can you immediately say, oh, that will be a class 4 cellular automaton? No, you cannot. That's eventually going to be a computationally irreducible statement. If you have a particular definition of classes of behavior, you will often have a situation where it is undecidable whether the system would satisfy that criterion. Like you could say it's class 2 if it just has stripes. It's class 3, class 4 if it has something which can be a localized structure that moves. Now, show me a localized structure that moves. Well, it may turn out that I have to go to an infinitely large size, an unboundedly large size, to find that structure that moves. And so that's, in that sense, it can be computationally irreducible or even undecidable what bin to put a particular cellular automaton into. Well, the same thing is true for a solid. If you're saying, does this solid with all its complicated molecules, do they arrange themselves into a crystal at a certain temperature? That will have the same problem, and I talked about that in connection with tilings last time from chapter 5, that whether there is a tiling that can be formed is something which is ultimately undecidable. And that's really the question of whether there is a crystal structure, for example, at a certain temperature that can be formed. And it's the same kind of story as in this case. So we have exactly the same issue. Sort of the analogy with solid liquid gas has an analogy even at the level of sort of the computational way of talking about this. Let's see. I talk about the frequencies of different cellular automaton classes as a function of the kind of the number of colors and the number and the range of the rule. And we'll see that class 3 tends to be dominant. And in fact, class 3 typically becomes increasingly dominant as you increase the kind of rule size of the rule space. It is interesting that there tends to be a sliver of class 4 that survives in all cases. It's not as if, as you increase the size of the rule space, that there are no class 4 things going on. There's still a certain percentage of those. Okay, I talk about let's see. I'm giving examples of these kinds of rules. I talk about, well, this undecidability question, about whether you can decide, given a particular criterion, what you can decide is going on, what class it is. Let's see, I think I talked about here the game of life cellular automaton. I think I have a much more detailed discussion of that on a different page. We'll come to that in a bit. I also talked about what happens for other systems other than cellular automata when you have random initial conditions. This has not been studied as much as it could have been. It's not quite as interesting in something like a Turing machine, because you can have random stuff on the tape, but the head may take a really long time to get to that random stuff. So it's not quite the same story as sort of randomness everywhere and what happens with it. Yeah, I mean, we talk here about multi-way systems and the fact that if you have an infinite number of initial states, things that becomes complicated. Now, footnote, 20 years later, Rulial multi-way systems, aka the Ruliad, is a story of a multi-way system with an infinite number of states. So I say here can't meaningfully be given an infinite number of random initial conditions, but actually now in the Ruliad, that limiting object that we think is underneath physics and mathematics and so on is in fact a multi-way system with an infinite number of states. But okay, let's go back here. Okay, we're now going to get on to another section. Let's go to our next section here. The next section is called sensitivity. Let me give you a scope of what we're going to be going through here. These are, we've just talked about these, the 4 classes of behavior. We're going to talk about sensitivity to initial conditions. Then we're going to talk about systems limited size. We're going to talk some more about class 3 systems. And then eventually we're going to talk about class 4 systems as well. So let's go through some of these. So sensitivity to initial conditions. Okay, let's imagine that you evolve one of these rules. Let's say it's a class 2 rule and it has a particular behavior. Now let's say you make a 1-cell change to the initial conditions for that class 4 rule. Okay, what happens in these different classes is characteristically different. And this is one of these places where, you know, is it a bird, a mammal, or a fish, or whatever? There are other properties that come with those identifications. So in the case of a class 1 cellular automaton, any change of the initial conditions just dies out, because after all, nothing is left, no information about the initial conditions is eventually left at all. In a class 2 cellular automaton, the change can persist, but it persists only in a localized region. In a class 3 cellular automaton, this is sort of a big deal and a defining feature of class 3, essentially almost any change it's an unstable system. Almost any small change that you make to the system will lead to an increasing region of change in the system. So you see that here, you just change that one bit there, and you get this kind of whole triangle of change. In class 4 systems, you get something where you may have change or you may not, and where these localized structures, in a sense, transport change across the system. In class 3 systems, change just inexorably grows. It's just, it's an unstable thing, so that sort of explosion progressively expands. But in class 4, things only expand if you kind of ride on a particle, if you ride on a localized structure. That's the only way that you can get places in class 4. Okay, these are class 3 systems showing what it really looks like to have that initial instability. Sometimes you will have a case like this is rule 30, where it grows at very constant speed on one side. On the other side, it grows at a smaller speed. It grows at a non-zero speed. It's always going outwards, but exactly how fast it grows depends on the characteristics of the rule. There's another example, that's rule 126, growing at speed 1 on both sides. Okay, so let's look at the class 4 case. This is the class 4 case. And as I said, if you're lucky enough to ride a particle, so to speak, your change can expand, but otherwise it may not. And so this is with different numbers of cells being changed. This shows the different kind of region of change that you get in the class 4 cellular automaton. Okay, there's a bigger version showing sort of more detail about what's happening. You can kind of see how the boundaries of this are determined by the positions of particles. Okay, let's go back here and take a look at some of the other things in this section. Let's see, some difference patterns we can very clearly understand. Curiously, that front on the side of rule 30 grows at a point about 0.252 cells per step, which is very similar but not the same as the rate of growth of the region when you start off from a single cell initial condition, the rate of growth of the region of randomness on one side as compared to the repetitive part. Okay, in an identification with other kinds of things studied in dynamical systems theory, Lyapunov exponents are the story of what one is seeing here. And what does that mean? In the case of, let's see if this talks about this. Okay. When we are looking at one of these systems, this notion of a Lyapunov exponent is something which came up in continuous dynamical systems, things with differential equations. You say, oh, this thing is becoming unstable. We've got two different trajectories in our differential equation that are made of these real numbers that are incredibly close together. These trajectories diverge over time. And the rate of divergence, they diverge exponentially in many systems. The rate of divergence is the exponent is called the Lyapunov exponent. And you can think about that divergence, that exponential divergence of trajectories. If you think about the digit sequences of the numbers representing those two trajectories, an exponential divergence is a kind of linear expansion in the digit sequence. So you're saying, it's affecting it by the ones column, the tens column, the hundreds column, and so on. It's linear in the digit sequence pattern and exponential in the value of the actual numbers. Well, in cellular automata, we directly see the quotes analog of the digit sequence in the configuration of cells. And so the Lyapunov exponent is just the actual rate of expansion of the perturbation in the initial condition that's here. So we can measure the Lyapunov exponent and say there's sort of a left and right Lyapunov exponent, and we can measure what it is. Now, interestingly, if we ask what is the Lyapunov exponent for rule 110, we'll realize it's actually not computable. We actually don't know. It depends on our definitions and what kind of limit we take and so on. It's a very complicated, squirrely thing to work out what is the Lyapunov exponent. No doubt there are continuous dynamical systems which have the same feature, that their Lyapunov exponent it isn't really an exponential story. It's a much more complicated story, and it's hard to tell what it's really going to do. But it's much more difficult to see those kinds of phenomena in a system where you are always worrying about whether you have some numerical round-off problem happening, because in a sense, the story of Lyapunov exponents rubs your nose right in numerical round-off, because what it's saying is when you have two trajectories that are very nearby, in the sense they differ only in, let's say, the 100th bit digit, well, if you're not using Wolfram language, if you're not using arbitrary precision arithmetic, you're just using machine arithmetic, then the 100th digit, you can't see that. That's just not something which is stored in a standard double precision floating point number. So it's very confusing. But that's something where you could, so in terms of digits, you're looking at these kind of high order digits, and it's kind of, you don't know whether your scheme for dealing with the digits and doing the computation is treating those digits correctly, and you've always got to worry about that. And so it's more difficult to define these ideas in continuous dynamical systems. But in cellular automata, the Lyapunov exponents are very, very, very clean. They're just the rate of expansion of a small perturbation in the initial conditions. And for example, some perturbations might grow, others might not grow. As soon as you have one that grows, you'll tend to have a single characteristic Lyapunov exponent on the left and right, unless it's a class 4 system, in which case it's very hard to define the Lyapunov exponent. Okay, so that's a little bit on sensitive dependence on initial conditions. We'll talk some more about that in chapter 7, when we talk about mechanisms for randomness and the ideas of chaos theory, which are very closely related to these questions about sensitive dependence on initial conditions, sort of amplification of small perturbations, and so on. Okay, next section here is about systems of limited size and class 2 behavior. Okay, so the cellular automata we've been talking about so far, they're all on an infinite line. They all just have cells that go off to infinity at the left and right. Let's imagine we didn't do that. Let's imagine that we just had things on a cylinder, where the cells are just looped around on a cylinder, and there's periodic boundary conditions. What will happen? So this section is about the general question of what happens in systems of limited size, and then talking about how that relates to class 2 cellular automata. Okay, here's a very trivial example of a system where you just have 6 positions, 0 through 5, and each one of these corresponds to a different rule for how you shift at every step. So this is just shift by one cell every step, and obviously when you reach the right-hand end, you'll wrap around to the left-hand end, because this is assumed to be a cyclic thing. If you shift by 2, you'll do this. If you shift by 3, you'll do this thing that has essentially period 2, and so on. And so what you see is, as a function of how much you shift, you'll see somewhat different behavior, from essentially period 2 behavior to this period 6 behavior here, and so on. So that's an example of a very simple system of limited size, and what it does is just addition of mod a certain number. Okay, let's see. This is the corresponding thing, mod 10 and mod 11, and you see slightly more elaborate patterns, but you still see the same idea of you're always seeing these kind of stripy patterns and so on. Okay, this is a more complicated case. This is a case where at every step, the position of the dot doubles. So we're saying it's position 1 at the left, and at every step, you just take the position number and you double it. And then you take that mod n. And then you ask what happens. And you can see it's somewhat more complicated here. Eventually, it always has to be periodic, because, well, if you've got the dot at a particular position here, it's a deterministic rule, so it always goes to the same position at the next step. But there are only a limited number of positions that it can be in, so the maximum period that it can have is the size of the system. But now you can ask, what is that maximum period as a function of the size of the system? And it's this rather complicated thing, and that turns out to have an interpretation in terms of number theory. It's the multiplicative order of 2 mod n, because this is multiplication by 2 at each step. But that is a number theoretical function with rather complicated behavior. Now, okay, so we can ask the same question for cellular automata. We can ask, if you have a cellular automaton like you have rule 90, and you just wrap it around in a register of limited size, so it has cyclic boundary conditions, and you start it off, let's say, just in one black cell. It doesn't matter where you put it, because it's a cylinder, so it's translation invariant. And you can ask the question, what will it do? So at size 16, for example, it just always dies out. Different sizes, you get different periods. So you see here, size 23, it's period 2047. Now let's look at rule 30. Same thing, at size 23, it's period 38,249. So now we can ask the question, as a function of size, what are those periods? And here we see the result. And the maximum possible period is determined by the maximum number of states that the system with n cells can have, which is just 2 to the n. So we can ask the question, how close do these get to having the maximal period? So for example, for rule 90, we're actually pretty far away from the maximal period. There's the maximal period. Here are the actual periods. Rule 45 is pretty close to the maximal period. Rule 30 is somewhere intermediate. It's going up at a fixed fraction, fixed logarithmic fraction of the maximal period. It's 2 to the power of something times n. So in the case of rule 90, it's 2 to the n over 2, roughly. In the case of rule 30, it's 2 to the 0.63 n, and rule 45, it's close to 2 to the n. Okay, so, and I say here, and I don't think anybody's really explored this further, that in the case of rule 110, the peaks seem to increase roughly like n cubed as a function of size. That's an interesting claim. I don't think that's been investigated, and one doesn't know why that would be true. But so what we're seeing here is this phenomenon that it could be in a class 3 cellular automaton, it could be something where you have period 2 to the n, you have some at least 2 to the constant times n as the period. Okay, so let's take a look. There are some pretty serious notes, I think. Huh, that seems like a bug. I can't believe there are really no notes for that page. It does seem like a bug. Something must have gone wrong there, because, yeah, this should be fixed. We'll fix it for its anniversary. Okay, here we're talking about cyclic addition. That was the first thing I was talking about. You just move a cell a fixed distance at every step. So at step t, the position of the cell is mod m times t, comma n. And the maximum repetition period is n over the GCD of m and n. And let's see, this is as a function of the numerical size of the quantity m over n. This shows the repetition periods. You get this rather nice kind of pattern of the maximum repetition period as a function of that rational number. And it's sort of a, it's very Pythagorean in some sense, in the sense of what the Pythagorean school was studying in terms of how repetition works and GCDs of numbers and so on. But this is sort of a summary of that as a function of the ratio. This is the repetition period, which is this n over GCD of m and n. Okay, cyclic multiplication. This is talking about the proof that it's multiplicative order of k and n over m. Piece of number theory there. Multiplicative order function is just telling you for which t, k to the t mod n is equal to 1. And that multiplicative order function always divides the Euler phi function. The Euler phi function gives you the number of numbers less than n. Euler phi of n gives you the number of numbers less than n that are relatively prime to n. So in other words, if you're taking fractions, you know, m over n, where m goes from 1 over n, 2 over n, 3 over n, etc., the number of those fractions which are in lowest terms is given by the Euler phi function. And that the multiplicative order function is some fraction of the Euler phi function. It always divides the Euler phi function. Okay, in the case of, what is this? Oh yeah, this is a slightly more complicated issue. This has to do with the Möbius mu function and the question of when you have how many states of a cellular automaton have what symmetry under rotation, because if you have something which is all constant, you can just rotate it around and at every position it will look the same. If you have something that goes 1, 0, 1, 0, 1, 0, there's sort of 2 different configurations of that relative to wrapping around the cylinder. And this is telling one about that, and the Möbius mu function is the story behind that. This could actually be written slightly more elegantly in modern versions of Wolfram language. Okay, additive cellular automata. This is sort of interesting. This was a thing that I worked on back in the early 1980s, together with Andrew Odlisco and Olivier Martin. There we go. Oh, look at that! I can find out the birth dates of my friends. The point about Rule 90. It's an additive cellular automaton. What does that mean? Remember, Rule 90 is the rule that says take the value of a new cell will be the sum mod 2 of the values of its left and right neighbors on the previous step. It's Pascal's triangle mod 2. But that can be represented in terms of algebra by saying the configuration of the system is given by a function, given by a polynomial, 1 plus, and then the coefficient of x to the n is, which is either 0 or 1, let's say that coefficient is equal to the value of the nth cell. And so then what happens is the evolution of the system at the tth step is 1 plus x to the t times the original initial condition, mod 2, but it's also mod x to the n minus 1. That mod x to the n minus 1 implements the boundary conditions. So this becomes a story of essentially polynomial powers. Instead of powers of integers, which is what gave us the multiplicative order function back with integers, this is powers of polynomials, mod 2, for example. And so one can do sort of similar analysis with the additive cellular automata as one could in the case of that simple shifting a number type system, or powers of a number type system. This is powers of a polynomial instead of powers of a number. Powers of a polynomial corresponds to the additive cellular automata. And we'll probably see more examples of that later. Those are comparisons of the periods of different rules, different boundary conditions that we can use, and so on. Okay, let's go to the next section here. So back to chapter 6, and the next section we're going to look at is about randomness in class 3 systems. So, as we said, when we have rule 30, here's what we get from random initial conditions. Here's what we get from a single cell initial condition. Well, you know, after it filled the space, it doesn't look any different, really. So what's happening is the force of randomness in something like Rule 30 is so high, it doesn't matter whether you start from it or whether you start from something completely non-random. The system injects enough intrinsic randomness that pretty soon what you see will be effectively random, whether or not it started from randomness. This is the phenomenon that I didn't understand really until about 1984. Even though I had seen this back in 1981, I didn't really understand the force of intrinsic randomness that happens in something like Rule 30 until that time. Well, so now, again, this is Rule 22. Rule 22 from a single cell initial condition produces just a nested pattern, but from a random initial condition produces this continued randomness. Okay, how does that really work? Well, if you keep looking at Rule 22 and you say, what with different initial conditions? Here it is with a single cell initial condition. Here it is with 2 cells there. Here it is with 3 cells. Here's a bunch of cells there. And here is the case of this particular pattern in the initial condition. And oh, whoops, it's unstable. It goes into this thing that is intrinsically generating randomness. It's symmetrical because the initial condition is symmetrical and the rule is symmetrical, but the behavior here, like Rule 30, shows the same kind of randomness. So Rule 22 is sort of an incipient producer of intrinsic randomness, just as Rule 30 is an immediate producer of intrinsic randomness. And we see that happening here. It's a very interesting phenomenon, which I think needs to be studied more. This idea that for simple initial conditions, you can end up with with sometimes having very easy to understand behavior and sometimes sort of falling into this pit of complexity and randomness. Now, Rule 90 is kind of special because it has this property of being an additive rule. So that means if we take, there's what it does from a single cell initial condition. If we have 2 separated cells, we'll see there are just 2 versions of that pattern, and where they overlap, they kind of just add in a simple way. And so in a sense, we'll never get this is a case where the randomness in the initial condition is really just being processed and represented on successive steps. We in a sense, don't get the same kind of intrinsic randomness generation for Rule 90. Okay. And this is what happens if you start from random initial conditions for Rule 22 and Rule 90. This is a phenomenon I thought was really kind of cool back in the early 1980s, when I was kind of studying the analogy between this and kind of statistical mechanics, thermodynamics, and so on. In the case of Rule 22, once it's random, it just stays random. In Rule 90, because its randomness is of this much thinner type that really depends on the initial conditions, what we see is these big voids, these big areas where it's recreating pieces of the initial conditions far down the pattern, even though there was a certain amount of randomness in the initial conditions. So that's a case where we're not really getting this sort of fully mixed random behavior. We're getting something which still has traces of its initial conditions. Okay. I talk here about some specifics about in Rule 22, what leads to that kind of random behavior as opposed to simple behavior. This is a case of Rule 225, another example, not studied as much as it could have been, where again, same phenomenon as in Rule 22, where you quickly get seeded with a block that leads to nested behavior, although it's this kind of logarithmic nested behavior ordinarily. But when you seed it in the right way, it'll suddenly produce randomness, just like these other kinds of rules. Rule 94, an interesting rule, much studied, sometimes produces nested behavior and sometimes produces seemingly random behavior. And those are other examples. This is additive cellular automata. You can have an additive cellular automaton with any pattern of how you add the cells up mod 2. I was thinking we had bigger versions of these pictures. They don't seem to be in here yet. Should check on that. Okay. This is a slightly more complicated note that asks, what is the generalization of additivity in cellular automata? For what rules phi is it the case of phi of u plus v is equal to phi of u plus phi of v? When does that happen? Does it happen only for mod 2, or is there another case that we can identify? Well, it turns out there are other cases. We can have the max of u and v. This is a case where you can have sort of additivity where the addition operation isn't a plus. And there are different commutative monoids that have, for which you can think of as sort of generalized plus operations, and you can start looking at different rules. And I have to say, I have not thought about this in more than 25 years. Gosh, this is kind of interesting. I should look at this again. This is relevant to some things that have come up in the physics project. This notion of generalized additivity and the kind of continuous version of generalized additivity and its relationship to Lie groups and things like this. This is interesting stuff. It's a good project for our summer school, I think. Okay, this is again something about, this is the thing every physicist will say, let's take what you've done in cellular automata with random initial conditions, and let's make a probabilistic estimate of how the cellular automaton behaves. I think I showed you before some notes from Dick Feynman about trying to do that for Rule 30, where he eventually said, okay, I believe you that this isn't something simple to work out. But essentially the idea is, let's imagine that the probability for a cell to be black is P, then the probability for a triple of cells to be black, white, white is P times 1 minus P squared, if you assume that the cells are independently black and white with that probability and have no correlations. With that probability estimate, you can do things like you can work out how will the density of the cellular automaton evolve with time, and what will the final density be? The final density will be one for which essentially P is equal to this polynomial that you get by probabilistically applying the cellular automaton, by applying the cellular automaton rule to this thing with probability P to be a black cell. Well, what happens is you get this mean field theory, as it would be called in physics, gives a somewhat accurate estimate. The actual density for Rule 22 is for random initial conditions is 0.35095. but what you get by a certain mean field approximation is 0.35012. But the question that you might ask is, well, is there a way of just systematically making that approximation better? I don't think that there is. I think it's not a thing that you can expect to have work, that these correlations that build up are, in a sense, increasingly complicated correlations. Actually, this is relevant for things we're thinking about right now in terms of chemistry, and thinking about molecular scale correlations and so on. This is an interesting example for that. So, all right, let's see what else is in the notes here. You never know what's hidden in the notes. The density of rule 90, yeah, that depends on the digit count function as a function of time. Okay, these are densities for other cellular automata, and this is asking the question, as a function of initial density, how does the final density, what determines the final density? And if you have a class 2 rule where the initial density determines how many things will turn into stripes, the final density can depend on the initial density. If you have a class 3 rule, it couldn't care less what the initial density was. It is intrinsically generating a certain behavior, and that's what will dominate the overall behavior of the system. Sometimes there are more complicated things that happen. There are density oscillations in rule 73. Those are more complicated kinds of things. Okay, let's go to the next section here. So the next section, we've got 3 more to go here. The next section is called special initial conditions. Okay, let's say that we have something like rule 30, and we say that generically, with a single cell initial condition, it produces randomness. With a random initial condition, it produces randomness. But can we find initial conditions for which it doesn't produce randomness? Well, here are some examples. If, for example, the initial condition is periodic with period 2, and it just goes black, white, black, white, black, white. Well, actually, the most straightforward case where it won't produce randomness is if everything is white. There's no black cells there at all, then the rule will make everything continue to be white. So obviously, it's not very random. Now, if we just say it's black, white, black, white, we'll again get something which is pure stripes. So with any given period, it's as if we had, as we lay it out periodically in the initial conditions, and we do that infinitely, that's really equivalent to just having cyclic boundary conditions. It's equivalent to having something, we just have all the cells looped around a circle. Okay, so we can ask the question, with different initial conditions, what different rules, what kinds of things happen? So there's rule 126. There it is for random initial conditions. There it is for special initial conditions, which in this particular case aren't just periodic, but they contain only blocks of the form 1100 and 1110. So in other words, it's being constructed from those special bricks effectively. Okay, so now this is asking for periodic initial conditions. The case of, this is a kind of a flip side question, which is if you want to get period P behavior, how big a block do you have to use to get it? So this is for rule 110, period 1. There's no period 2, can't be done with rule 30. Period 3, period 4, period 5, period 6, period 7, period 8, and so on. All these different periods, and for example, to get period 11, a 275 cell block is required. So it's not proved, but it seems likely that you can get all periods, or maybe I did prove this for rule 30. I'm not sure actually, whether you can get all periods. Let's take a look at the notes. Let's see. This is asking the question, for period P, to achieve period P, how large a block do you need to achieve period P? Okay, the length of blocks is at most 2 to the 2p. Okay, so I think it is possible to get it for sufficiently large p. These are This is just details about how you do that. And these are pictures showing just how long do you have to, for some periods, you can't find a block that does it, but eventually, but for other periods you can. And the maximum size of block, if you can do it, is 2 to the 2p. Okay. Oh, that's interesting. Okay, that's a different discussion. That's repetition in systems based on numbers. I kind of forgot that note that talks about iterative maps and things like this. Okay, in the case of iterative maps, there's a thing called Tsiolkovsky's theorem that says that if you get period 3 occurring with this repetition with numbers, then all periods must occur. And I've been curious whether any such similar result holds for cellular automata, and so far I haven't been able to find that, but this is kind of the run-up to that kind of result. This is talking about the correspondence to the renormalization group, which is a methodology in physics. Let's go back to the main text here. Let's see, what is the fastest way back? I think I just have to go back through here. Okay, so we're talking about special initial conditions here. We've talked about the special initial conditions which lead to periodic behavior. Now, here are special initial conditions which lead to nested behavior, for example, and or lead, actually, this is a slightly different thing. This is asking, under what circumstances will one rule behave like another rule? So now this is saying, if we take rule 126, and we take always pairs of black cells or pairs of white cells together, then rule 126 will behave exactly like rule 90. We can see that here, in this case, the pair, the blocks that go black, black, something else, you map those blocks to a single cell here, and you can see that rule 126 emulates rule 90, where a 1 in rule 126 turns into this, where a one if you use 1 in rule 126, that's equivalent to a single 1 in rule 90. So it's kind of like a very, very minimal compiler. We're saying you want to take rule 126 and get it to emulate rule 90. Rule 126 can do all kinds of things that aren't what rule 90 can do, but it can do what rule 90 can do. All you have to do is start it off with initial conditions where the rule 90 configuration has been compiled into this black, black, white, white initial condition for rule 126. So it's kind of like a run-up to being like a universal computer, but this is a very simple case where we're just looking at fixed blocks for the emulation of one cellular automaton by another. This is a case of rule 90 emulating itself at a different scale, and in a sense you can understand the self-similarity of rule 90, the fact that it produces a nested fractal pattern, by the fact that there is this kind of emulation of the rule itself by the rule under this kind of blocking transformation of just taking every other cell to be black. Okay, this is an example, that's the same thing for rule 150, showing that it has a nested behavior because it is invariant under this transformation that takes sort of an autoencoder for the rule. It takes a cell. Again, it will emulate itself. Okay, rule 184, which has very interesting properties, has phase transitions and things, again has that property. I'd completely forgotten it did this. With 3-cell combinations, it will do this self-emulation kind of thing. Actually rather interesting. Okay, there's an example of rule 184 showing kind of the way that you can make a nested pattern from this by having a nested initial condition that will, most of the time, nested initial conditions are nothing special. They just produce complete randomness. But rule 184, because it has this sort of self-similarity property of the rule emulating itself, when the blocking transformations will preserve nesting in this kind of way. Okay, that's a random initial condition showing how it produces these kinds of it gradually cancels out the black stripes and the white stripes. I would say that rule 184 which I just thought was kind of an interesting rule, turns out to be the standard minimal model of road traffic flow in modern times, where there's kind of free streaming cars and there's cars that are stuck in traffic jams and so on. I had worked on road traffic flow long before I even worked on cellular automata, and the fact that cellular automata ended up emerging as a model for road traffic flow is really, really kind of cool, even though I didn't particularly make that connection. I just studied the cellular automaton for its own sake. Okay, here's a slightly more elaborate cellular automaton, that slightly more complicated rule that has a lovely pattern that shows the same kind of nested structure that rule 184 shows, starting again from random initial conditions. Kind of has a three-dimensional feeling to it, although it's just a two-dimensional pattern. And I don't know why this is going so slowly. Okay. All right, so we talk here in the notes to the section on special initial conditions about Tsiolkovsky's theorem I had mentioned. I would say you can compute for additive cellular automata. It's rather elaborate, but you can actually compute the fractal dimensions are always algebraic numbers that or logarithms of algebraic numbers, and this is the computation for those algebraic numbers. Oops, what do I do here? That's not what I want. Back here, okay, rule. Oh, I don't even show the pattern. That's no fun at all. I say that rule 45 leads to a nested rule 90 pattern when it's starting from a background of repeating 110 blocks. A single black cell on a background of 110 blocks. Should I actually show that? Let's just do one experiment here. So let's say I say center array of, what has happened to this computer? Something is very weird is going on here. Oh, wow. Something that's running super, super slowly. 110. And I think I want to say, do the right thing? Oh, I didn't do the right thing. I have to remember how this works. Okay. Okay, here we go. So let's say 500 of those, and let's say array plot of cellular automaton 45. Oops. What did I do wrong here? This should be, oh, silly me. Okay, let's say 200 steps here. Okay. Well, I kind of got it a little bit messed up because of the way that the initial conditions work. But you see, this is rule 45, and you can see there's very characteristic rule 45 behavior there. But look at this. There's a nested piece to it. It's a slanted version of the rule 90 pattern. So even from within the complexity of rule 45, there is a special, there is a slice of reducibility that you see in that you see there. And this is kind of, in a sense, this section can be talked about in terms of this notion of slices of reducibility within otherwise irreducible systems. This is a question of uniqueness of cellular automaton patterns, and the question of if you ask to go between when you have a block of cells, what does it take to get that block of cells? It's kind of an inverse question. This is square root of rule 30. Nested initial conditions I talked a little bit about. Okay, let's go back to the main event here. We got two more sections to go through. The next one is called the notion of attractors. Attractors have become more exciting in a sense in the intervening years because they're kind of the big story of machine learning and neural nets. It's kind of like you've got many, the notion of an attractor is there are many different initial states which will lead to a single final state or a single group of final states. And the attractor is that group of final states that everything leads to. And the basin of attraction is the set of states that lead into that particular attractor. So in this case here, this is, we're starting off from all possible initial conditions. This is a class 1 cellular automaton, and we're always ending up in this one attractor. Here's a class 2 cellular automaton where we have a whole bunch of attractors, but there are many initial bits here that we could add in and they wouldn't affect the final state. So these are examples here where these are different initial conditions, but they don't affect the final state. And so that means that all those different initial pieces of data, they could all be pictures of a cat, and they all have different pixels in them, but they all come out to say it's a picture of a cat. They evolve to the same final attractor. Well, we can characterize this. This is a slightly more elaborate thing. We can characterize different, when we try to characterize these whole sets of possible configurations which can occur in cellular automata, we could ask the question, we can say, there's this finite state machine where we say, as we walk along this initial condition, we say we can go along one edge or the other edge, and every possible initial condition is made from going along some sequence, some path in this finite state machine. And then you can ask the question, as you evolve the system, how will that finite state machine change? And this is a way of characterizing these infinite configurations that we get and looking at essentially the way that the attractors build up here. And so this is sort of a characterization of how the set of states that you get, you have all possible initial states represented by this finite state machine where paths can go any black, white. And then that gets more and more complicated as the set of configurations that can occur is characterized by this more and more elaborate finite state machine. And in class 3 systems and class 4 systems, those finite state machines, this is another characterization of the complexity of class 3, class 4, that those finite state machines rapidly become very, very complicated. And that's another way of sort of understanding class 3-ness and class 4-ness and so on. Here are examples for rule 30, starting from, and rule 90, starting from an initial state, which isn't all possible initial states, but one characterized by that finite state machine, showing how more complicated it gets. Let's see, going back here to the notes in here, there's a lot to say here about attractors. Let me go through these fairly quickly. Cellular automaton case. Finite automata, we can ask the question. It's a very interesting question. I still don't know the answer to this. How many finite automata are there of size n? Because there is a notion of different finite automata. There are minimal ones, and there's a question of how many minimal ones are there of a certain size. That characterization of the set of possible states in a cellular automaton after t steps is always governed by a path through a finite graph. Finite automaton means that those are regular languages. And they correspond to regular expressions. We can characterize the sequences that we get by regular expressions, which we can represent using the pattern language of Wolfram language. We can also do generating functions. And let's see if we've got some pictures here. This is a notion of which blocks of cells are excluded. Okay, this is the thing, maybe I shouldn't go into this. This is a connection to dynamical systems theory and the notion of entropies and dimensions in cellular automata. We can ask the question, if we look at a sequence of length n, and we look at blocks, I'm sorry, we look at all possible sequences that you get in the cellular automaton, and we look at blocks of length n. The question is, for a block of length n, how many possibilities are there for that block of length n? If all sequences of cells are allowed, it's 2 to the n possible blocks of length n. But often there will be redundancy, and so the number of sequences will be much less than 2 to the n. It's like letters in English, for example. Because U always follows Q, the entropy of English, the information content of English, is much is smaller than the maximum value. So if we normalize it to 1, we can say for English it's about 0.5, and we can ask for a cellular automaton what correlations are there between the black and white cells that will cause it to be the case that a block of length n has less than 2 to the n possible configurations, perhaps 2 to the h times n, where h is what we would call the entropy. And so we can work that out for a variety of cases, and we can find out what those entropies are. There are zeta functions. That's a more elaborate dynamical systems theory idea. There are, oh yeah, this is interesting. This is two-dimensional generalization where you look at a patch of cells and you ask how many possible patches can occur, because the cellular automaton, all the cells in the patch are determined by the beginning of the patch and the walls of the patch. That means that there's a limit to the number of possible configurations that can occur there. You can look at probabilistic entropies as well as, this is kind of Shannon entropy versus other kinds of entropies and so on. More elaborate discussions about, this is the question, more elaborate discussions about cellular automata which have maximal entropy and so on. This is the story of, this is actually a cellular automata was studied in the 1950s in connection with cryptography, and actually it's a little bit out of date these days, DES cryptography, which used to be kind of the standard for cryptographic systems back in the 1980s and so on. The S boxes, the sort of substitutions that happen inside DES cryptography, was kind of obscure in general how those were determined. And I think they were determined through looking at what amount to cellular automata that have certain the property that they are that every configuration of a cellular automaton has a unique predecessor for a finite size cellular automaton. Okay, this is asking the question. I talked about how many of the possible blocks of length n that occur spatially. You can also ask the question, how many possible blocks of length t occur temporally? And there's a relationship between the number of blocks that can occur spatially, the number of blocks that can occur temporally. They're related by the Lyapunov exponent, by that maximum rate of growth of a perturbation. The space-time patches. This is a bunch of the history of this. Let's see. I think I talked about those iterated maps, attractors in Turing machines. Okay, these are things that's a good topic to study again. Hasn't really been looked at. Okay, this is a good page, a good note. This has to do with state networks. So if you have a system of finite size, limited size, you can draw a state transition diagram that says, for example, let's say we just have numbers 0 through 5. We can just say, when you add 1 to each number, you're just going, step 1, 2, 3, 4, 5, and then you go, there's the mod, there's the wraparound there. You redraw that graph, you get just, this is the structure of the state transition diagram. In the case where you're going in hops of 2, the state transition diagram breaks into 2 disconnected components. In the case where you are doing, let's see, this is the case where you're doubling at each step. And there you see more complicated state transition diagrams being produced. You can do a state transition diagram also for a cellular automaton. You're asking where every dot in this diagram represents one configuration, one complete configuration of the cellular automaton. So there's rule 30. And what you see in rule 30 is that there's a big attractor basin. There are many states here that all lead down to this repeating state here. And so that means that much of all the 2 to the n possible states of size, let's say 2 to the 9 possible states of size 9, what we get here is most of those states are transients that evolve down to states which eventually will be the periodic state. And we can kind of see this overall pattern here that eventually, for example, let's say size 15, there's a single big attractor, and then there's a basin of attraction here. Size 16, there's 2 big attractors with different basins of attraction here. Rule 45, different behavior here. In Rule 45, you see the attractor is a much bigger part of the story for most sizes. And that's reflected in the fact that it's the maximum, the size of the cycle, because the attractor is kind of vacuuming up all of the states here, the size of the attractor is close to 2 to the n. Okay, there's a bunch of stuff about group theory and the application of symmetries to these kinds of things. These are looking at the kind of number theory of what's going on. These are, for additive cellular automaton rules, there's a very nice algebraic theory of the state transition graphs that you can get. If you just pick a network at random, you can ask the question, what will be the structure of the state transition graph for a random network? And there's all kinds of things about the fraction of nodes that have no predecessor is 1 over e, the exponential constant, and so on. Okay, let's go. So that was something on attractors. These are kind of summaries of the attractors, this notion of you can start from all possible initial conditions, and this is kind of in the section on starting from randomness. This is the case where you start from all possible initial conditions, but you evolve down to an attractor that contains only some subset. In the case of a class 1 cellular automaton or class 2 cellular automaton, the attractor is very obvious in the spatial structure of the system. In the case of class 3, it's not so obvious, but it becomes a subset, but that subset is also able to support class 3 behavior. And so that's what it means to have an attractor in that kind of case. Oops. Okay. The final section of chapter 6, structures in class 4 systems. Okay, so class 4 systems, their characteristic feature is that they have localized structures. So here we see some examples of class 4 systems. It's really a remarkable thing. I mean, starting off from just complete randomness here, sort of order emerges, and it's these complicated structures. Sometimes they die out, sometimes they just are repetitive, sometimes they propagate, these persistent structures, localized structures. This is what's happening here. So these are different examples of class 4 cellular automata. And if we ask the question, let's look at all possible initial conditions. This is the code 20 cellular automaton with next nearest neighbors and a totalistic rule. Most of the time, it either just dies out quickly or it produces this thing that I always used to nickname the death module. But sometimes you end up, like with initial condition 151, you end up with a periodic structure, initial condition 187, you end up with a propagating structure, and so on. And so you can ask for this rule, you can say, well, okay, these are the structures. Well, what structures can occur? And it's an interesting zoo. These are structures which essentially solve the equation of some power of the cellular automaton applied to this initial condition, some power of the cellular automaton rule comes back to the same thing again. But for example, in this case, this is period 22, the initial condition 195 as a binary number, generates this pattern with period 22. Sometimes the initial condition is part of the pattern. Sometimes there's kind of a leader, like in this case here, there's a leader that goes through a transient before you get the full pattern. But in this case, to get period 5, what we're seeing here, these are all the structures that have small period that exist. These are all the structures that can be produced by small seeds, by small collections of cells in the code 20 cellular automaton, going up in this case to 256 millionth initial condition. So we can think of these as kind of the particles that propagate information across this particular cellular automaton rule. Okay, so it turns out that there is a systematic way. If you know the period you're looking for, there is a systematic way using that finite state machine sort of technology that I mentioned earlier. There's a systematic way to find all possible configurations of a cellular automaton that have a given period. It gets exponentially more difficult to do this as you increase the period, but you can see the results here for some period. So for example, for period 10, there's this huge sized object which has period 10, but we can find it by these methods. And so we could imagine at period, some big period up here, suddenly there could be some comparatively simple case, or maybe what happens is as you go to these other periods, well, we know already from the previous picture that there are some high periods here, like period 22, that has a very small seed that will generate it. But so that's a question of what happens with these different structures. Okay, so let's look at a different rule. let's look at, this is code 357, another famous rule. This is a totalistic rule with 3 colors. Here are its persistent structures, the first few, and let's keep going. What do we find next? Well, bit of a surprise we're going to come to next. There's more persistent structures. Oh, I'm sorry. This is, we're now looking at code 1329. Code 357, that was all we knew on the previous page. On code 1329, here we have a bunch of structures that are like, well, this is a rather ornate structure, which is ultimately just a thing that propagates across the page with a fixed period. This is one which has a very long transient, but eventually leads to that structure there. But now we go a little bit further, and sort of big surprise here, this is a structure in code 1329 that just grows forever. So this is something, if it was like Game of Life, this would be called like a glider gun. It's producing, well, these are really not gliders because they're not moving, but this is something where starting from this initial condition, 54,889, suddenly at that initial condition, things grow forever. It's kind of as if in the early Earth, you have all these sort of chemicals floating around in sort of prebiotic soup, and then suddenly there's one that sort of arranges itself to grow forever. And this is sort of, it's unlikely, but it happens. And the grow forever one could even take over the whole system. And that's, so it's sort of a surprise, and it's kind of the long arm of computational irreducibility and undecidability is reaching in, and it's saying, you just look for these different initial conditions and you'll never know what's going to happen. It follows my mantra, you know, the computational animals are always smarter than we are. This is one of those examples where you keep looking, you say, this is just going to produce periodic behavior, this is just going to do this. Oh, whoops, it does something completely different. Okay, let's look at a few other examples here. This is, oh, more of 1329. Yeah, okay, so these are more things that grow in 1329, and you'd say, oh, well, it's going to produce these elaborate things. Oh, no, actually, with this initial condition, it produces just a simple uniform pattern. And there it produces one that goes on both sides. It doesn't always have to produce just these periodic structures. It can just be, it's kind of like a you know, it's a metastatic thing. It just suddenly starts growing forever, and it grows in a very simple way in this particular case. Okay, let's look at a few more examples here. This is the simplest of the class 4 cellular automata in terms of the size of the rule. This is rule 110. Started from a random initial condition. And you see it's a little bit more difficult technically to deal with because it has this repeating background, has a period 14 background here. And it's a block of 14 cells repeating every 7 steps as the background, but superimposed on that background are kind of these defects. It's kind of like a crystal, and these are crystal defects that are running around inside the crystal on top of this background. And we see here these different kinds of particles, these different kinds of persistent structures. We can look here at what persistent structures exist. Here are known persistent structures in rule 110. There are some that are extensible. You can just keep going. You can keep repeating that same structure, but here they are propagating to the left, propagating to the right, and so on. This is kind of the zoo of structures you get. Now, if you keep going further, you will find a growing without bound structure. Here it is. This is important in the proof of computation universality in rule 110, but this is something where it produces these 2 different kinds of localized structures, 2 different kinds of particles on each side. You see here, the sort of the stem cell keeps going, producing these different kinds of particles. What can you say about these particles? Well, you can do particle physics with this. You can look at the interactions between particles, and there's a whole calculus of what happens when you collide 2 particles. Sometimes they'll basically just pass through each other with a phase shift. That's exactly what you would see in particle physics. It's kind of an elastic collision with a phase shift. And then sometimes there'll be an inelastic collision, and you'll get different particles produced. So it's kind of all a story of something like particle physics. Here are more complicated examples, same kind of thing. 2 particles come in, these are 2 particular particles, and just changing, essentially, in particle physics, it might be changing the momenta, changing the phase shift. You get different kinds of outcomes from these different rules, from these different collisions. Remembering, of course, that all these collisions are completely deterministic. That is, every time you run this particular collision, it'll run the same way. Here's a pretty elaborate set of collisions. Look at all that stuff. You just come in with the two particles and you get this whole elaborate story of what's happening here. I've always thought it would be nice to kind of make a movie where you see all these different things going on and maybe there's some music playing behind it and you see all these structures and they're interacting in different ways and you kind of might be rooting for one particular structure and you might have some whole emotional connection to these structures. And in the end, it is revealed that this movie is just a cellular automaton running according to deterministic rules and with a particular initial condition. And everything that you read into it is a matter of you reading things into it. And that kind of tells one something about the nature of our kind of perception of the world and so on, and how that works. Let's see, okay. Let's just look at the notes for this section. There are questions about kind of the halting time. If you start off from different initial conditions, what is the halting time? What is the distribution of halting times? That's kind of an interesting question. This is about the background for Rule 110. This is about some of the details about the structures in Rule 110, the collisions and so on. This is the example of the game of life, two-dimensional cellular automaton where lots been studied about these structures and we know what some of the periodic structures are. Those have been increasingly filled in over the last 20 years. A lot is known. It's kind of a complicated and interesting story of kind of meta-engineering. It's kind of like progressive engineering of different kinds of structures in the game of life. And it's interesting to see that over the period of 50 years. It's interesting to see when you have one of these, what is this called? This is the puffer train. This is something which, look, a slice of it looks just like Rule 1329, although Rule 1329 is a lot easier to deal with than this. But that's kind of the residue from that puffer train. You can think about that in the space-time slice in terms of something that's very much like Rule 1329. This is more like the kind of the simple case of Rule 1329 looked at in space-time history and so on. Let's see, is there anything else here? That is it for chapter 6. So chapter 6, starting from randomness, that was a little bit of a summary of what's in it. I would say that I have to say it's been a while since I looked at this in detail. I'm just continually reminded there's a lot of stuff here, and there's a lot of interesting things, some of which have been investigated over the last 20 years additionally, and many of which have not. And there's a lot of things which, as I rethink about them, they provide examples of phenomena like slices of computational reducibility within a background of computational irreducibility, like the finding of sort of computational irreducibility and sort of and the story of the principle of computational equivalence and its robustness of the fact that all these different systems, random initial conditions, simple initial conditions, particular cases with particular initial conditions, and so on, it's once you see not obviously simple behavior, you're in the same bucket of equivalent computational sophistication. And that's kind of the empirical run-up to the principle of computational equivalence, which we'll talk about in more detail in chapter 12. All right, I think that's everything I had to say here about chapter 6. So if there are questions or comments on that, I'd be happy to try and address them. Okay, let's see. Let me just try to okay, William is saying for Rule 110, the growth is polynomial. Well, it depends how you count it. This is a question of kind of how, in a cellular automaton, linear growth in a cellular automaton is exponential growth in the number of different cell configurations you can reach, because a length n cellular block of cellular automaton cells is a 2 to the n possible configurations of those cells. So that's kind of the relationship between like length in the cellular automaton and size in the state space of the cellular automaton. RBS is asking, do you know which rules make random behavior, and do you know, and how can you tell from the rule itself? There's a little bit you can tell from the rule itself. You can tell whether the rule itself is always going to grow, is always going to make a pattern grow. It's just like if the rule itself says whenever there was a white cell here before and it's going to turn into a black cell when there's a neighboring black cell, that's a clue that it's going to grow the pattern. But to know for sure whether it's going to produce, for example, random behavior, absolutely not. That's a story of computational irreducibility, undecidability. It's absolutely not something you can tell directly from the rule. And you can see that in cases where, like Rule 22, where for some initial conditions, it doesn't produce randomness. For some initial conditions, it's a nice, simple, just pure nested pattern. And then you have to keep going for a few different initial conditions, and eventually, bam, it starts producing randomness. And that's kind of a sign that it's going to be an undecidable story of whether you actually even get randomness from a particular rule. So this inability to know what rules are going to lead to in terms of their behavior, this is kind of the quintessential feature of computational irreducibility. William is asking about black holes as attractors. Attractor in a literal sense. Well, yes, it's an attractor in the spatial sense. It's the question of what it looks like in state space, where we're usually talking about, okay, this is a complicated story. I mean, you can think about some mountainscape where, you know, or some just a function of X and Y, height as a function of X and Y, and you think about a ball rolling around and then it rolls down to the minimum. Think about a mountainscape, sort of the water runs down to the attractors and the lakes and so on. Yes, those are a perfectly reasonable story of attractors. And the GD6 around a black hole, yes, they lead into the black hole, and it's an attractor in that sense. Just as the paths down the mountain, so to speak, lead to the lake, or they might lead in that case to a local minimum lake, you know, a mountain lake, so to speak, rather than to the global minimum. But those still count as attractors. They are places where the paths end up. Let's see. There's a question from Brady here about whether, if you have if you've put down a pre-existing collection of black and white cells in the plane, and you ask the question, can you make a rule that sort of tries to modify those cells based on the future as well as the past? I think you've basically got a two-dimensional cellular automaton at that point, because you've got a notion of time progressing, and you've got this whole configuration of past and future. Now, you could also imagine something where it is progressively sort of rewriting the cells that are in the future. Yes, that's kind of, I've looked at that a little bit. That's kind of like an inhomogeneous cellular automaton, more like a spin glass kind of analogy in physics, where you've got some initial configuration, where you've got the background has some particular featuring in it, but it's not been studied as much as it should have been. Let's see. Hector is asking, cellular automata evolve vertically according to deterministic rules, but if we read horizontally, well, in the case of something like Rule 30, starting off from a single black cell, reading horizontally or reading vertically, you will see randomness, so to speak. What happens in other cases where you have a random initial condition and then you sort of read horizontally, that's what this whole classification of cellular automata is about. What do you see? Do you see something that looks simple? Do you see something that looks random? That's kind of that whole story. David is asking about continuous systems and Gödel's incompleteness theorems. Well, Gödel's incompleteness theorems actually relate not to continuous systems, but to the Peano arithmetic's axiom system, which is about integers. You can construct real numbers that actually has more straightforward, in some ways, decidability properties. This is a complicated story, let me not segue into this story because it's really not so relevant to the story of chapter 6. Okay, Memes is asking, have you noticed cellular automata that display Penrose tiling characteristics? In a sense, the Penrose tiling has the feature that you can't tile with those tiles periodically, but you can tile on a nested pattern. And yes, many cellular automata produce nested patterns, and even produce ones that, if you want the geometry of the Penrose tiling, that's a slightly different story. And that's not something you're going to get on a standard lattice like this, that's more on a pentagonal lattice or a pentagonal approximation to a lattice. But again, slightly different story. There's a question here from 6751. Who's asking about, can you assign meaningful values to something that's truly random? Come back next week. Chapter 7 is mechanisms of programs in programs in nature, and it is specifically the first section of it is called, well, actually, second section is called 3 Mechanisms for Randomness, and it is about exactly these kinds of issues. Question here, would the path from a random matching follow from a shortest path rule? This is asking, Luis asking this, maintaining the lowest entropy. I don't quite understand that question. Yeah, I don't quite understand that question. And I think we ran out of time here. So, well, thanks for joining me. And next week, we'll talk about Chapter 7, Mechanisms in Programs in Nature. And I encourage you to check out the actual book, which, as I showed, is all online and so on. And you can also actually, in this section, the Wolfram language code to implement the kinds of things being talked about in this section is extremely straightforward, just using the cellular automaton function, and check it out. And try, it's amazing that even among the elementary cellular automata, so much that isn't known. What does Rule 225 do with seeds that cause it to have random behavior? What can you say about the random structure of Rule 22? What can you say about the apparently cubic increase of the maximum period for Rule 110? So many questions, and we're just at the very beginnings of answering these questions, and they're very accessible to computer experiments and to sort of careful experimentation, like experiments in the real physical world. The experiments, computer experiments, it's all a question of how organized, how well and how clearly do you think through what you're doing. But I encourage people to try some of these things out. And we are increasingly, we're moving towards having our Ruleological Society as a place to collect all these kinds of people and the projects that are done in this area of ruleology, studying the behavior of systems with simple rules. All right, well, that's it for now, and hope to see you another time.